Hello. Okay, let's continue. Akara, can you hear me?
Yes, sir.
Good,
Clear,
good.
sir.
Very good. If you can hear me, I just want to make sure that you can hear me and it's recording. Good. So guys, in the previous example, we just actually have kind of introduction to eigenvalues and eigenvectors. As you see, to solve that problem, you need to have some knowledge about computing determinants. So in this section, we'll talk about determinants. And tomorrow, maybe we'll talk about 4.3 and on Friday, 4.4. And hopefully we'll cover everything about this chapter in this week. And once again, you will have quiz next week, most probably Tuesday or Wednesday. And after that, October 12th, you will have final exam. It is from 4.1, 4.2, 4.3, 4.4, and 5.1, 5.2, 5.3, 5.4. So these 8 sub-chapters you have to study for your final exam. So this chapter for your final quiz. Anyway, so what we have here we have, first we'll start with determinants and determinants of n by n matrices, how they calculate them, the Laplace expansion theorem, properties of determinants, determinants of elementary matrices, determinants of matrix operations, Cramer's rule, and the adjoint proof of the Laplace expansion theorem. Now, a lot of this, some theorems here, proving it really takes a lot of time. I'm not going to do that, maybe some short theorems to give some idea. We will prove it here. Here, the main purpose is to be able to calculate or compute n by n, determinants of n by n matrices. And you have to also be familiar with some properties of determinants. That is our purpose of learning this part of the chapter. Now here, as you see here in these examples, instead of this rectangular brackets, we just put, what is it, parallel lines or line segments, whatever it is, or vertical lines. So here, when we just, instead of using this rectangular brackets, we just use this vertical bars actually to denote the determinant. So here we just call this determinant of this 3 by 3 matrix, that's equal to 0. And the determinant of this 4 by 4 matrix is equal to 0. Actually, they represent something, they mean something. So here we'll just get, try to get some idea about how do we evaluate these determinants. First, before we starting this, as you know that if you're given 2 by 2 matrix, let's say here we have A, B, and the C, D, right? When we actually studied how to find the inverse of the matrix, there we actually studied also how to find the determinant of A. Or that is simply, I just use this, 2 vertical bars, and that's equal to, what is it? How did they define this? That is AD minus B times C. So now we know how to find the determinant of 2 by 2 matrices, right? It's just A times D minus B times C. In a similar way, I'm just giving a definition here. How about if you're given 3 by 3 matrix here? Then the determinant of A is the scalar. It's just a number, one number. And either using this or this, depending on the context, which one is more convenient, you can use both one of these, either of these notations. So that's equal to A11. And here we have just started here A11 times A22, A23. How do I get getting this thing? So actually, I'll just give a special name to this. To obtain this one, I'm just deleting this column and this row. And what is that here? A22, 23, A22, 23, A32, 33, A32, 33. And the second, and pick this element, component, A12, and delete this column and this row. What do we have here? A21, A23, A31, A33, right? Plus, the first one is minus, and the second one is plus. A13 in a similar way, just pick this component and delete this column and this row. And this is how we are defining What is this? The determinant of 3 by 3 matrix. For example, immediately, for example, if you're given this matrix now, let's say 1, 2, 3, let's say here we have 0, 5, 2, 1, 6, let's say here we have 7. How to calculate this determinant by this definition? First, starting from 1, right, is 1 times, delete this row and this column. What do we have here? 5, 2, 6, 7. Here we have 5, 2, 6, 7. Now it is minus. The second component is 2. Delete the column that contains 2 and the row that contains 2. 0, 2, 1, 7. 0, 2, 1, 7. And here we have plus, the third component is 3, and delete this column and this row, 0, 5, 1, 6. And here we have 0, 5, 1, 6. And we know how to evaluate 2 by 2 matrices determinants. So it is 5 times 7, 35, right? Here we have 35 minus 12, so that's equal to 23, minus 2 times, here we have 1 times 23, 2 times 0 minus 2, that is minus 2, plus 3 times, here we have 0 minus 5, so that is just minus 5. That's equal to 23 plus 4, 27, minus 15, that's equal to 12. So the determinant of this matrix is 12. Okay. So now let's use another, let's just write the previous one in another way. So determinant of A. Here, let's see here, what is this? This is just determinant of that thing, right? So I'm just giving a special name. How am I obtaining this? The kind of submatrix here. It's a determinant of this submatrix. So if I just write this one as A11, what is A11? It is a submatrix obtained by deleting the first row and the first column. This 1 and 1 means deleting the first row and the first column. And how about this one? Since here we have 1, 2, so that's also 1, 2. How did we obtain this submatrix? Deleting the first row and the second column. And this one is 1, 3. How did you obtain this submatrix? We just obtained by deleting the first row and the third column, right? So actually, we just give a special name. That is called, actually, this determinant of this ij is called the ij minor of A, my matrix A. So as you see here, when I just write in this form, it looks more compact. A11, determinant of A11, that is ij 11 minor of A, 1, 2 minor of A, 1, 2 minor of A. So by using sigma notation, as you see here, the second subscript notation changing here, right? This is 1, it is 1. And here we have 2, here we have 2. And here we have 3, and here we have 3. And that's why I can just write with sigma notation. Here we have the second one. So it is, let's say, because I'm going to use I for the first subscript notation, J is changing from 1 to 3. And see here, the sign is changing. It is plus, minus, plus. If you have more, then always it is plus, minus, plus, minus, plus, minus. So here we have negative 1. The first one is plus, so here we have 1 plus j times, and this component that is A1, the first subscript notation is changing, the second one is changing, so 1j times, here we have determinant of A1j. Okay, because on purpose we are writing this, because when we are talking about the matrix of bigger size, writing in this way is not so practical. So this one is, you can just express this in a more compact way. Okay, that is minor. Also should keep this in mind. Ij minor of A, what is this? Just determinant of Aij. How did you obtain this? By deleting ith row and the j's column. All right, another example, compute the determinant of A. So how do you do that? So immediately to compute this one, we know that determinant of A and is equal to just a thing is equal to, first here we have 1. I don't have to write this. So here we have 4025 minus, and here we have 1. So also I don't have to write 1. It is delete this column and this row, 3015 3015 plus, and here we have 2, delete this column and this row, 3, 4, 1, 2. So here we have 3, 4, 1, 2, which is equal to, the first one is 4 times 5 minus 0. That is 20 minus 15 minus 0. Here we have 15 plus 2 times, it is 6 minus 4. That's equal to 2, which is equal to 5 plus 4. So determinant of this matrix is 9. And this is how we compute the determinant of 3 by 3 matrix. So now let's just give a definition to n by n matrix. So determinants of n by n matrices. So let's A be this matrix ij, whose components are given by this ij. Be an n by n matrix. Here n is greater than or equal to 2. Even actually, also it works for 2, even it works for 3. So especially here, we are just writing this for bigger matrices, because now we know how to calculate 2 by 2 matrices determinants, right? And also 3 by 3 matrices determinants. Anyway, then the determinant of A is the scalar. That's determinant of A, or this A in this parallel bars. That's equal to, here we have A11, determinant A11, minus A12, this plus, minus, plus, minus, plus, minus, right? And just simply here, so since we have n columns, this j is changing from 1 to n. So here we have j changing 1 to n. So since the sign is also alternating here, -1 at first starting with positive, positive, negative, positive, negative. So here we have -1 to the power of 1 plus j. And here the components in the first row, A1j, determinant of A1j. That is ij minor of A. That is how we evaluate the determinant of any matrix. Okay, so as you see here, each time here we have, that's 1, here we have -1 to the power 1 plus j times determinant of A1j. Actually here, instead of this one, I can actually use another notation, another labeling here, that actually here I can just write this in a more compact form then. So let's say that it's called cofactor of A. What is cofactor of A? It's just defined as the product of these two things. Cofactor of this ij cofactor of matrix A is here -1 to the power of I plus j times determinant of ij. Simply just this, as you see here, each time when we're calculating determinant, these two things appear, right? So instead of writing these two things, I'm just defining this as Cij, just introducing new label. Okay, but which one is because you'll see that in a lot of examples, writing in this way is actually just helps us to write our big expressions in very compact form. Anyway, so when it is so, now how can I write a determinant in a more compact form? At the time, that is how we evaluate this determinant, right? It is -1 to the power of 1 plus j. So here, instead of this, -1 to the power of 1 plus j, and here we have determinants, this a1j, right? That's just minor ij. So here, it takes this form. It looks much, much simpler. Just a1j, cij. What is cij? It's ij cofactor of a. So now, Laplace expansion theorem. That's the power of theorem. As you see here in our definition, all the time we were just expanding or evaluating or computing the determinant along the first row, right? But actually, in general, you can evaluate this determinant using any row components or any column components. Okay, this is about this theorem. I mean, this theorem is about that. It says that the determinant of an n by matrix A, where n is greater than or equal to 2, can be computed as this. Determinant of A equals A I1, C I1, A I2, C I2. What is I? Actually, this is I's row, right? So you can just use the first row or the second row, the third row, fourth row, right? So it doesn't matter. It just gives us the same results, okay? Which is the cofactor expansion along the ith row. We're just computing the determinant by cofactor expansion along the ith row. And also, determinant of A, here we have 1j, 1j, 2j, 2j. What is, it's not, column is not changing, right? But here rows are changing. So that is by the cofactor expansion along the j's column. And what it says. So here, just let's say here, if you start from here, plus, minus, plus, minus, plus. If you start from here, minus, plus, minus, plus, minus, plus. If you start from here, plus, minus, plus, minus, plus, minus. Okay. So let's just see one example for that. Compute the determinant of A by cofactor expansion along the second row. So the second row is here, right? So it means, as you see here, second row is started with minus, minus, plus, minus, plus. Actually, because from here I can just know that C, right, I, J is equal to, what is it? Negative 1 to the power of I plus J times determinant of A, I, J. And so here, starting from here, the second row means here, that means that the first one will be 1, 2, because 1 plus 2 is 3, 3 is negative 1 to the power of 3, determinant of A, 1, 3. That's why we are starting here with minus. Once you know just one side, we know that it alternates, then it is minus, plus, minus, plus, minus, plus. So to do this one, here, question A. Okay, guys, let me change the color. That's that one. How about purple? I don't know how it looks in black white boards. Not bad. Not bad. Cofactor expansion along the second row. So determinant of A by second row, right? What is it? It is just A to 1, C to 1 plus A to 2, C to 2, right? Plus A to 3, C to 3, right? Now I know that it's actually here it is minus, plus, minus, plus, so that is equal to, what is A2? 1, it is 1. So here we have 1 times, actually it should be minus because the first one is minus. So here, delete this row and this column. So negative 3, 2 left. Here we have negative 3, 2, and negative 1, 3. Negative 1, 3. So the first one is minus, second one is plus. A2, 2. What is A2, 2? It is 0 times, delete this row and this column. So it is 5, 2, 2, 3. 5, 2, 2, 3. I'm just writing this because when it is 0 even, I don't have to write this since it's just a warm-up example. Next one is minus, right? And now minus, here we have 2. So that is A, 1, 2, 3. So we have to delete this column and this row. What is that here? 5 minus 3, 5 minus 3, right? And 2 minus 1, 2 minus 1. Okay, the first one is minus 9, minus minus 2, that's minus 7. With this minus, it is 7. Second one is just 0 minus. Third one is, here we have 2 times 5 times negative 1, negative 5, minus minus 6, it is plus 6, so that is 1, which is equal to 5. So the determinant of this matrix is 5. A second method, how about if we use, oh, it's too dark. I think we need to use something light. Okay. How about part B? In part B, cofactor expansion along the third column. So that's the third column, right? So third column is here, this plus, minus, plus. So it's just start with plus because it is 1 and 3. 1 plus 3 is 4. So it is plus, minus, plus. So determinant of A is starting from here, right? That means that here we have A 1, 3, that is 1, 3, C 1, 3, plus A, the second one is 2, 3, C 2, 3, plus A 3, 3, the third component, that is C 3, 3. So since I know that the first one is plus, because 1 plus 3 is 4, negative 1 to the power of 4 is 1, so equals, so it will be plus, minus, plus. So here we have A1, 3. What is it? It is 2. And here we have delete this column and this row, 1, 0, 2, minus 1. So 1, 0, 2, minus 1. So this will be minus 823, that is 2, and delete this column and this row. 5 minus 3, 5 minus 3, 2 minus 1, 2 minus 1, plus, now the last one is 3, so delete this column and this row. 5 minus 3, 5 minus 3, 1, 0, which is equal to 2, and just calculate this, negative 1, so here we have negative 2, minus 2 times minus 5 minus minus 6, so that is 1, plus 3 times, it is 0, minus minus 3, it is 3, which is equal to minus 4 plus 9, that's equal to 5. Let's see, here we get the same answer, it doesn't matter. So we have the same answer. Okay, so that is how we evaluate this. Of course, here you must have already realized that now which way, actually, which one, or cofactor expansion along actually which row or which column is the best way. And the answer is so simple. Which row or which column contains the most number of zeros? And you have to use that row to compute the determinant of the given matrix, because you don't have to do a lot of calculations. Now, in this example, compute the determinant of the matrix is given below. First, if you look at this, as you see here, this column, right? This column contains a lot of zeros. So I want to calculate the determinant of this matrix by cofactor expansion along the third row. So, sorry. So here we have it is plus, minus, it is plus, good. So now, what is determinant of A? If you just compute this by cofactor expansion along the third column, because of this 0, it will be 0, 0, 0, 0. So, right, so we don't have to write the 0 because, okay, 0 times something is 0, 2 times something, 0 times something is 0, 0 times something is equal to 0. So only, I should just take this 2, it is plus, so this will be minus, because this one is 2, 3, right? 2 plus 3 is 5, negative 1 to the power 5 is negative 1. So here we have minus 2, and here, what is cofactor of this? So I should delete this column and this row. So what do we have here? Here we have 2, negative 3, 1, and here we have 1, minus 1, 3, and here we have 2, minus 1, 0. Now, equals negative 2 times. So as you see here we have 0. Again, I can just actually compute the determinant of this matrix by cofactor expansion along the third column or third row. Which one is easy for you? Let's just use the third row. So this one is plus, minus, plus, so this will be plus. So here we will have, okay, here we will have, let me just write here like this. So here we will have 2 times, right? Delete this row and this column. So here we will have minus 3, 1, minus 1, 3. Okay, not like this. Just put this. Now it is plus, so this will be minus. Minus 1, it is just plus, because of 1, we don't have to write this. So here we have delete this row and this column. What we have here, 2, 1, 1, 3. 2, 1, 1, 3. And the third one is 0, so that's why we don't have to write this. Equals, here we have minus 2 times 2. Here we have minus 9, minus 1, it is minus 8. So here we have minus 16, plus it is 6, minus 1, it is 5, which is equal to minus 11, minus 2 times minus 11, that's equal to 22. So determinant of A is 22. And how about B? How about determinant of B? Maybe I should use different colors so you can see that these are different questions. How about determinant of B? Okay, and here only the first row contains 0. Let me just use this one. So it is 1. So here we have plus, minus, All right, let's compute the determinant by cofactor expansion along the first row. So here we have 1. We don't have to write this. So here we have, what is it? Delete this row and this column, 1, 1, 1, 1, 1, 1. And here we have 2, 1, negative 1, 2, 1, negative 1, 1, 1, 2, 1, 1, 2. Minus, the second one is 2, delete this row and this column, okay, 2, 1, 1, 2, 1, 1, negative 1, 1, negative 1, negative 1, 1, negative 1, 1, 1, 2, 1, 1, 2, right? 2, 1, 1, negative 1, 1, negative 1, 1, 1, 2. Okay, it's also done. Plus, now here we have 1. Okay, we don't have to write this 1. So delete this column and this row. What do we have here? 2, 1, 1, 2, 1, 1, minus 1, 2, 1, minus 1, 2, minus 1, and 1, 1, 2. Okay, so we have to evaluate these determinants. Now we know how to evaluate these determinants. We have just practiced here, right? And you can just do this and write your answer here. Okay, I will just leave this for you to practice this because we have already done this. I just put this example. How do we evaluate the determinant of 4 by 4 matrix here? Okay. So how about in this case, you will see that compute the determinant of A. What is this? If you actually recognize this, it's just upper triangular matrix, right? So all the entries, right, under the main diagonal, they are zeros. So at the time, so if I just evaluate this determinant along the first column, I just need to write this 7, right, and then write this matrix. No, the first column and 5, write this matrix, submatrix 1. So if you're given either lower unit triangular matrix or upper triangular matrix, what is the determinant of this one? Since all the components under the main diagonal, they are 0, just determinant is equal to the product of the components in the main diagonal. So that's equal to 7 times 5 times 1 times 8 times 1. 7, 5, 1, 8, 1, which is equal to 35. 8 times 35, that's equal to 280. I guess 8 times 30, 240, plus 8 times 4, 5, 40. Your sum is 280. So actually, we can just give this as a theorem. Then determinant of a triangular matrix is the product of the entries on this main diagonal. Specifically, if A is this matrix, then determinant is equal to A11, A22, ANN. These are all just the product of the components in the main diagonal. Okay. Guys, I will finish by this theorem. Maybe we'll prove some of them tomorrow, okay? Since we do not have much time, some lectures, classes, I'm going to make a video at night time and share with you. So you have to just watch all the videos. I put them under one channel, that is linear algebra, as you know, okay? So if you have any questions, anything that you want to discuss, you should just let me know. One day earlier, we can arrange the time and have discussion. So properties of determinants. Anyway, let's say we are given a square matrix, n by n matrix. Number 1, if A has a 0 row or column, then the determinant of A is equal to 0. It's not difficult to, how to say, understand this, because if you just compute the determinant along by cofactor expansion by that column or by that row, since all components are 0, it will be equal to 0. Second, B says that if B is obtained by interchanging 2 rows or columns of A, then determinant of B is equal to minus determinant of A. Right? For example, let's say, just a simple example, we are given A, whose components are A, B, C, D. And I'm given another matrix. The only difference is just these rows are interchanged. So here we have C, D, and AB. Now, if you just calculate this, it is AD minus BC. How about this one? BC minus AD. So here it's saying that if this matrix is obtained by interchanging only two rows of this matrix, then determinant of A is just equal to minus determinant of B. That is the second property. Third one, if A has two identical rows or columns, then determinant of A is equal to 0. Let's say here we have AB and also here we have AB. Two rows are the same. Right? It contains two rows which are exactly the same. Then we don't have to evaluate the determinant. It's always equal to 0. So if B is obtained by multiplying a row column of A by K, then determinant of B is equal to K times determinant of A. Okay, for this, it's like for 2 by 2 matrix. Let's say we just multiply, it says multiplying a row or column. Let's multiply a row here. It is K times A, K times B. And here we have C and D. And what is the determinant of this one? If you calculate this, K times AD, right? Minus K times BC. So K is a common factor. We can just take this out. Okay, if one single column or single row is multiplied by K, so determinant of B is equal to just K times determinant of A. Okay, if A, B, and C are identical, except that the ith row or column of C is the sum of the ith row columns of A and B, then determinant of C equals determinant of A plus determinant of B. That is homework for you. Just try to understand, else tomorrow I'll show you some examples. If B is obtained by adding a multiple of one row, column of A, to another row, column, then determinant of B is equal to determinant of A. Well, the last one, this one again, if you just consider this matrix, let's say this A, B, C, D, right? And here I obtain B, and it's saying that how? Obtained by adding a multiple of one row column to another one. Let me just multiply this by K and add here. So what we have here, that here we have A, here we have B. I multiply the first row by K and adding this to the second row. So here we will have C plus K times A. And here we will have D plus K times, what is it? D. No, K times B. Right? So now, let me just write determinants, okay? Okay, also here determinants. You don't have to write it again and again. So we know what is this determinant? It's AD minus BC. How about this one? That's equal to A times D plus KB minus B C minus KA. So if you just simplify this, here we have AD minus B times C, BC, right? Plus here I have AKB or ABK. And how about here minus why this, it should be plus, right? Here we have minus BKA, ABK, which is equal to AD minus BC, which is equal to determinant of A. Okay. So we have more examples. I will continue from here. I don't know, maybe if I can make a video, I'll share with you. As you know, guys, we don't have much time, and I'll go a bit faster. As I told you, for quizzes 4.1, 4.2, 4.3, 4.4, and for final exam 4.1, 4.2, 4.3, 4.4, and 5.1, 5.2, 5.3, 5.4. You have to prepare for those sub-chapters. Okay, thank you very much. See you tomorrow. Bye-bye.